All right, so let me put this in slideshow. So what we're going to talk about is just a little bit of review, okay, and then I'm going to do that crazy phase change diagram that I put through on the board today. So temperature versus heat. Remember, temperature is dealing with the kinetic energy of motion. So it takes all of that kinetic energy and gives you the basic average kinetic energy of the particles in a substance. Heat is how the temperature flows. So heat flows is the energy, okay, as it flows from a higher temperature to a lower temperature. Okay, so that's the difference between those. All right, you have to remember, okay, you should know the SI unit for Kelvin. I'm not going to worry about that. But thermal energy, it's the total amount of energy you have. So all of the chemical potential energy, the energy that's stored in the molecules before they're doing work, and the kinetic energy, okay? The kinetic energy once the chemicals are mixed together and their temperature is increasing, etc., or they're doing work, okay? All right, thermal energy relationships. As I increase temperature, you guys remember, I'm going to increase my thermal energy because my kinetic energy is being increased. Okay? If my temperature stays the same and I have a more massive substance, so substance that has more mass, the thermal energy is going to be higher, okay? Because it's the total measure of energy. So I wanted to make sure that's clear. All right, heat flow. Heat, the flow of thermal energy. Okay, so that energy, that total energy of kinetic and potential energy, flowing from one object to another, and remember, has to flow from a temperature difference. It flows from warmer to cooler objects. So here's a perfect example. The cup gets cooler while the hand gets warmer. Okay, it's flowing from warmer to cooler objects. The ice gets warmer while the hand gets cooler. All right, specific heat. Some books call it S. We have known it as C, so don't get confused with that. Okay, so specific heat. Things heat up or cool down at different rates. Remember, specific heat is taking 1 gram of substance and how much heat is required to raise it 1 degree Celsius. So land heats up and cools down faster than water, and we're definitely lucky for that. Okay. All right. Oh, here's the nice 1 kilogram, 1 gram, same thing, okay? All right, and we know what the specific heat is. All right, water. Water's water, have a high specific heat. I'll just throw this in here for you. Okay. You got to remember there's that strong bond attraction between your water molecules, and the water molecules are attracted to each other and they're connected to each other with hydrogen bonds. Okay, so it's going to take more energy to break those hydrogen bonds. Versus, remember, your metals have those weak bonds. They have those C electrons, so it doesn't require as much energy. But that's why water has a high specific heat capacity. I'm not going to ask you that question, but in general, you should know the difference. Okay? All right. The Q, the M, the delta C, the C. Okay? I don't care which way it is, MC delta T and delta TC, doesn't matter. Okay? Q is the change in thermal energy. Okay? Remember, thermal energy changes because there is a change in temperature. Mass of the substance, change in temperature, and C, which we'll call C, CP, don't stress out, is specific heat of the substance. Okay? All right, if 25 grams of aluminum cools from 310 degrees Celsius to 37 degrees Celsius, how many joules of energy are lost by the aluminum? Okay? You would have to know the specific heat, and this is in... They've converted it to Kelvin, or I guess I'm not sure why, but anyway, regardless, specific heat here because they used joules per gram degrees Kelvin. Okay, but anyway, Q is equal to MC delta T. Okay, so all I would do is plug it all in, and Q is negative, which means heat is being lost. It's transferred out of the aluminum. Okay, don't panic. I won't give you a problem with degrees Kelvin, but you should know how to find the heat. Okay. All right, here's now where we start getting into the phase change information. Heat can be transferred even if there's no change in state. Okay, so even if I'm still a solid hanging out, okay, heat is definitely transferred. Okay, there's energy that's being transferred there even if my temperature doesn't change. I'm sorry, even if my state doesn't change. So let me rephrase that. So solid, I'm still a solid whether I'm at negative 32 degrees, negative 22 degrees, negative 12 degrees, I still have a solid. Okay, there's still heat being transferred. I still have a solid material until I get to that typically 0 degrees, and that's when I start the melting process. Okay, so it's just telling you that energy can be transferred in the form of heat even if there's no change in state. Okay. And then the heat transfer can cause a change in state. So here's an example where we're going to talk about the heat of fusion and the mass. So remember, if there's a phase change, solid to liquid, liquid back to solid, etc., your temperature is relatively constant. So you can't use Q is equal to MC delta T. Okay? So you have to use the heat of fusion times your mass. And remember the heat of fusion, there's just a standard chart for that, so we'll give you that on your test or quiz. Okay. Requires energy liquid to vapor. Okay, yes. Okay, I'm going to skip this. All right, so let's look at this equation. Q is equal to heat of fusion times mass. So why do I need this if I have this Q for the heat transferred or the heat absorbed, etc.? Okay, remember, when there's a phase change, there's no change in temperature, but there's a change in energy. So when I go from 1 to 2 or 2 to 3 or 1 to 2 to 3, I have to account for all of the energy for the entire phase change and the other phases in between. Okay? All right, so if I want the total heat it takes to take ice, turn it into steam, there's 3 steps. Okay, so let's go through them. The first step, I'm going to melt the ice. Okay, so if I'm melting ice, I'm assuming I'm starting at 0 degrees Celsius. If I start below 0 degrees Celsius, I have to use Q is equal to MC delta T. Okay, so I'm starting at 2 on the level on my chart. Okay. I'm going to show you the chart in just a second. Let's see, can I pull it up? I think it's back here. All right, so I'm starting here at 0 degrees Celsius. Then I'm going to go to 3. Okay. Then I'm going to go to 4. That's what I'm trying to do. Okay, so let's go back. Okay. So at 2, then I'm going to move from 0 degrees to 100 degrees Celsius. So now I need the heat transferred. So I'm going in between the liquid phase. And then I'm going to hit the heat of vaporization. So here's what we're going to do. I'm going to show you this. Okay. All right, let me skip this and I'll come back. Okay. So here's the first phase. I'm starting at 0 degrees Celsius. Okay, look at my chart here. I'm going to melt at 0 degrees Celsius, but I'm not going to change temperature. So I can't use equation 1, 3, and 5. So I have to use the delta H of X times M. And X is referring to either fusion, solidification, it's referring to vaporization or condensation. So when I go from a solid to a liquid, when I start that melting process, that is called delta H of fusion. Okay? So what I'm trying to do, the delta H of X is always in joules per grams. Multiply it by my mass, that gives me my energy for just that part. Okay? So when I have a phase change, I don't have change in temperature. So let's look at Q. Q, I'm trying how much heat is required to melt 500 grams of ice and heat water to steam at 100 degrees Celsius. Okay? So Q is 500 grams times 333 joules per gram. That is a value that we will give you. Okay? That gives you the energy needed for the phase change of the whole melting process. Okay? Now the second part I need is the liquid phase right here. And it goes from 0 to approximately almost at 100. Okay. Here I'm changing temperature, so I can use Q is equal to MC delta T. So let's go back. So I'm raising from 0 degrees Celsius to 100 degrees Celsius. I'm dealing with liquid water, so my grams don't change. And then you find a change in temperature with T final minus T initial, okay? And this should say Celsius. I'm sorry. I don't know why it doesn't say that. Now, the C for water, for liquid water, we know is 4.18 joules per grams degrees Celsius, okay? So this gives me the energy of 2.1 times 10 to the 5 joules. Now we're going to be evaporating because that's what it's asking us to go to steam. Oh, whoops. Okay, so I'm going to steam. So right here. I'm going to the steam right here. Okay, so because I'm going to steam, here's where I'm steaming at 100 degrees Celsius, then there's no change in temperature. So here, Q is equal to 500 grams times 2260 joules per gram. That is a value that is the heat of vaporization. Again, it's a constant value that we'll give you. And that gives me those joules. Then what I do is I take all of my joules together and I add them up, and that's what I get. Okay. So now what I want you to do is pull out that worksheet, make sure you're understanding everything. So let's look at this graph just one more time. If my temperature is below 0 degrees Celsius, I have to start with equation 1. So if it is negative 17 degrees Celsius, I'm going to move from negative 17 degrees Celsius to 0, just like that worksheet says. So that's the first phase. And then from 0, let's say I want to move to 85 degrees Celsius. Then I'm going to go from 0, I'm going to phase change and melt, and then I'm going to heat. So I'm going to go through 1, 2, and 3. Okay. The important part to remember about this, and of course I'll be here to ask questions, is you have to look at your difference in temperature. So if I had a negative 17 degrees to start, negative 70 degrees Celsius, my final temperature, because I'm going from 1 to 2, is 0 degrees Celsius. So final minus initial, 0 minus a negative 17 degrees Celsius is equal to 17 degrees Celsius. So I plug that in as Q is equal to MC delta T. Okay, that's how I would find 1. Then to go through my phase change, I'm going to go with the heat of fusion times my mass. Okay. Then to go to, I don't know what I said, 85 degrees Celsius. Then to go to the liquid phase, I'm going to use Q is equal to MC delta T. Okay. If you have any questions on this, we'll go through it in class tomorrow again. That I just wanted to make sure you had a video. There is this worksheet with all of your answers online, okay, already posted for you. You need to come see me Friday at 7:30, or you need to come see me Monday at 7:30 if you have questions. Bye-bye.